Welcome to Lecture 5 of our flow matching tutorial series. This is where theory meets practice. Over the previous lectures, we built the complete flow matching recipe, from velocity fields and probability paths, through the mathematical toolkit, to the training algorithm with all its extensions. We now have everything we need in theory. Today we go fully practical. We will walk through a complete working implementation on the 2 moons dataset, the running example we have been building towards since Lecture 1. We will discuss architecture choices, noise schedules, sampling strategies, and survey the real-world applications that have made flow matching the dominant approach for generative modeling at scale. Let us see where we stand in the lecture series. In Lectures 1 and 2, we built the foundations. Velocity fields push distributions, and neural ODEs let a network define a velocity field. In Lecture 3, we designed probability paths, the straight-line trajectories that connect noise to data. In Lecture 3b, we built the mathematical toolkit, sampling, expectations, conditional expectations, and the MSE gradient linearity property that makes training possible. In Lecture 4, we put it all together into the flow matching algorithm, the CFM loss, the marginalization trick, training and sampling code, conditional generation, and data couplings. That gives us the complete theoretical recipe, but knowing the recipe and cooking a great meal are two different things. Today, in Lecture 5, we go fully practical. We will walk through a complete working implementation, discuss architecture choices like UNets and diffusion transformers, explore noise schedule design, analyze the quality-speed trade-off in sampling, survey state-of-the-art systems like Stable Diffusion 3, FLUX, and MovieGen, and compile a debugging guide for common failure modes. By the end of this lecture, you will have a concrete understanding of how to build, debug, and scale a flow matching system from toy experiments to production. Let us start with the complete end-to-end implementation of flow matching. This is the running example we have been building towards since Lecture 1, transforming a Gaussian cloud into the 2 moons distribution. The code has 2 parts, the training loop, which we already saw in Lecture 4, and now the sampling loop, which completes the picture. The model is a simple feed-forward network with 3 hidden layers and ELU activations. It takes the concatenation of position xt and time t as input, and outputs a velocity vector. Nothing fancy, just a standard MLP. Training is the 5-line loop from last lecture. Sample data x1, sample noise x0, sample time t, interpolate to get xt, compute MSE between the network's output and the target velocity x1 minus x0. That is the entire conditional flow matching loss. Now look at sampling. We start from pure noise, 512 points drawn from a standard Gaussian. We take 100 Euler steps, each of size 1 over n. At each step, we evaluate the learned velocity field and move each point in that direction. After 100 steps, we arrive at samples that match the 2 moons distribution. The entire thing is 30 lines of code, requires no external OD solver library, and trains in about 30 seconds on a laptop. This simplicity is the core appeal of flow matching. One of the great strengths of flow matching is that it is completely architecture agnostic. The loss function does not care what kind of neural network you use. It only requires that the network takes a position and a time and outputs a velocity vector. In our toy example, we used a simple MLP. But for real image generation, 2 architectures dominate. The first is the UNet, which has been the workhorse of generative modeling since 2015. It uses an encoder-decoder structure with skip connections. Time is injected through sinusoidal embeddings and feature-wise linear modulation layers. Spatial attention is added at low resolutions. This is the backbone behind DALL-E 2, Imogen, and Stable Diffusion versions 1 and 2. The UNet is well understood and proven, but it becomes difficult to scale cleanly past about 2 billion parameters. The second is the Diffusion Transformer, or DEET, introduced by Peebles and Xie in 2023. The idea is simple. Patchify the image into a sequence of tokens, then process them with standard transformer blocks. Time conditioning is done through adaptive layer normalization. This is the architecture behind Stable Diffusion 3, FLUX, Sora, and MovieGen. The key advantage is that it scales cleanly with compute. Just like language models, and it can leverage the entire LLM infrastructure, flash attention, fully sharded data parallel, and all the other tricks that have been developed for large transformers. The essential point is that flow matching does not constrain your architecture choice. The loss is always the same MSE between predicted and target velocity. The architecture only determines how much capacity you have and how well you scale. Now let us talk about noise schedule design, which is one of the most important practical decisions in flow matching. Recall from Lecture 4 that the affine conditional flow is psi t of x given x1 equals alpha t times x1 plus sigma t times x0, where alpha t and sigma t define the scheduler. The scheduler controls how quickly the interpolation progresses from noise to data. The table shows 4 common choices. The conditional optimal transport schedule, which is the simplest, alpha t equals t, sigma t equals 1 minus t. This gives you straight line interpolation. The polynomial schedule generalizes this with alpha t equals t to the n. The linear variance preserving schedule uses alpha t equals t and sigma t equals the square root of 1 minus t squared, which keeps the norm roughly constant. And the cosine schedule uses trigonometric functions for a smoother transition. There is an important theoretical result here, the scheduler equivalence theorem. All these schedulers produce the exact same samples at t equals 1, in theory. If you trained a convergence with infinite data, it does not matter which schedule you use. But in practice, it matters a lot. Different schedules lead to different training dynamics. Some put more weight on the noisy regime near t equals 0, others on the clean regime near t equals 1. And the discretization error at finite sampling steps differs too. Straighter paths, like conditional OT, generally need fewer steps. My practical advice: start with conditional OT. It is the simplest, produces the straightest paths, and works well in most settings. Only switch to cosine or variance preserving if you encounter training instability or if you need compatibility with pre-trained diffusion model checkpoints. Let us now see how these affine conditional flows look in practice using the flow matching library from Meta. On the left, you see the training code. The library provides affine prob path and condo path as convenient wrappers. You pick a scheduler, call path.sample with your time, source, and target samples, and you get back a path sample object that bundles xt, the interpolated point, t the time, and dxt the target velocity. Then you just compute the MSE loss between your model's prediction and the target velocity, exactly as we have been doing. The library handles all the alpha t and sigma t bookkeeping for you. Want to switch from a cosine schedule to conditional OT? Just change one line. The loss computation stays the same. On the right, you see something particularly powerful: post-training schedule change. Remember the scheduler equivalence theorem from the previous slide? Because all schedules produce the same samples in theory, you can train with one schedule and sample with another. The library's schedule transformed model does the conversion for you using the scale time transformation from the paper. This is useful in practice. You might train with a variance preserving schedule because your dataset works better with it, but then switch to conditional OT at sampling time because it needs fewer steps. Or you might inherit a pre-trained diffusion checkpoint that uses a VP schedule and want to sample with OT paths. The key takeaway is that the library abstracts away the mathematical plumbing and lets you focus on the important decisions: what data, what architecture, what schedule. A critical practical question is, how many sampling steps do you need? This is where flow matching has a major advantage over traditional diffusion models. The plot on the left shows the classic quality-speed trade-off. Quality, in blue, increases rapidly with the number of steps but then saturates. Speed, in red, decreases linearly since each step requires evaluating the neural network. The sweet spot is somewhere in the middle, typically around 20 to 50 steps for flow matching with OT paths. Compare this to DDPM, which originally needed 1,000 steps. Why the dramatic difference? Because OT paths are straighter. When the paths from noise to data follow near straight lines, each Euler step introduces very little truncation error. You can take large steps without drifting off course. Curved paths, on the other hand, accumulate error at each step, requiring many small steps to stay on track. On the right, you see the hierarchy of ODE solvers. Euler is the simplest, one network evaluation per step. Midpoint uses 2 evaluations per step but is significantly more accurate, so 25 midpoint steps give roughly the same quality as 50 Euler steps. RK4 uses 4 evaluations and is even more precise. Adaptive solvers, like Dopre 5, automatically choose the step size based on error estimates. My practical recommendation: start with Euler at 50 steps for prototyping. Switch to midpoint at 25 steps for equivalent quality with fewer total network evaluations. Use adaptive solvers when you need the best possible quality for a final model. We discussed data couplings in Lecture 4. Now let us see how they work in practice, specifically the Minibatch optimal transport coupling. With independent coupling, which is the default, each noise point x0 is paired randomly with a data point x1. This means paths can cross. One noise point far to the left might be paired with a data point far to the right, while a nearby noise point gets paired in the opposite direction. These crossing paths create a curved velocity field that the network has to learn, requiring more capacity and more sampling steps. Minibatch OT fixes this. Within each training batch, you solve an optimal transport problem to find the best pairing between the B noise points and the B data points. Best means minimizing total transportation distance. This produces nearly parallel, non-crossing paths within the batch. The computational cost is cubic in the batch size using the Hungarian algorithm, but for typical batch sizes of 256 to 1024, this is negligible compared to the neural network forward pass. The diagram on the right illustrates the difference. With independent coupling, the arrows cross and curve. With Minibatch OT, they run roughly parallel. The empirical results are compelling. Minibatch OT consistently improves FID scores by 10 to 30% and reduces the number of sampling steps needed by roughly a factor of 2. This was shown by Tong and colleagues in their 2023 work on conditional flow matching. The practical recommendation is simple: always use Minibatch OT unless you have a specific reason not to, such as paired data where the coupling is given. Let us now look at how flow matching has been scaled to state-of-the-art image generation. The two most prominent systems are Stable Diffusion 3 and FLUX. Stable Diffusion 3, released by Stability AI in 2024, uses a multimodal diffusion transformer, or MMDIT, that processes text and image tokens in the same sequence. Crucially, it uses flow matching with OT paths, not traditional diffusion. The interpolation is the rectified flow formula: xt equals 1 minus t times x0 plus t times x1. Models range from 2 to 8 billion parameters. It typically uses 50 sampling steps with a classifier-free guidance scale of about 7. FLUX 7 from Black Forest Labs, also released in 2024, pushes this further. It uses a hybrid DT architecture with both parallel and sequential attention blocks. The flagship model FLUX-F7.1-Dev has 12 billion parameters. What makes FLUX particularly impressive is that through guidance distillation, they created FLUX. It also uses rotary position embeddings borrowed from the language modeling world. The architecture diagram at the bottom shows the common pipeline. The input image is encoded into a latent space by a VAE encoder. The DT, or MMDIT, performs the denoising in this latent space, conditioned on text embeddings from a text encoder like T5 or CLIP. Finally, the VAE decoder maps back to pixel space. This latent space approach is critical for scaling. Working in the latent space of a pre-trained VAE reduces the dimensionality dramatically, from millions of pixels to thousands of latent tokens. This makes the flow matching training and sampling computationally feasible at high resolutions. Video generation is where flow matching truly shows its practical advantages. Video is enormously expensive because you are generating not one image, but many frames that must be temporally coherent. MovieGen from Meta in 2024 is a 30 billion parameter DT-based model that uses flow matching with linear OT paths. It can generate 16-second videos at 768 by 768 resolution and 16 frames per second. It also does joint text, audio, and video generation. The model uses temporal attention across frames to maintain coherence. Other major video generation systems that use flow matching or closely related approaches include Sora from OpenAI, which generates roughly 1-minute videos at 1080p, VO2 from Google DeepMind, Cog Video from Tsinghua, and Mochi from Genmo. Why does flow matching excel at video? 3 reasons. First, straight OT paths mean fewer sampling steps, which is critical when each step involves processing hundreds of frames. Second, the OD-based sampling is deterministic and reproducible, which matters for production workflows. Third, working in a latent space dramatically compresses the temporal dimension. The fundamental scaling law for video is simple. Video generation cost equals image cost times the number of frames. Any reduction in the number of sampling steps directly multiplies out across the temporal dimension. This is why flow matching's efficiency at inference time is the key enabler that makes tractable video generation possible. A method that needs 1,000 steps per frame is simply not viable for generating 256 frames. But 20 to 50 steps per frame, that is practical. Flow matching is not just for images and video. It has become the dominant approach across a remarkable range of domains. Let me highlight 3. First, protein design. FrameFlow and FoldFlow use flow matching on the special Euclidean group SE3 to generate 3D protein backbone structures from scratch. The state space is a product of SO3 for rotations and R3 for translations, one for each amino acid residue. This is a natural fit for the manifold extension of FM that we will cover in Lecture 6. These models achieve state-of-the-art designability scores, meaning the generated structures can actually fold into the predicted shapes. Second, speech and audio. VoiceBox from Meta uses flow matching for speech synthesis. Instead of generating audio autoregressively token by token, it generates entire speech segments in parallel, conditioned on text and surrounding audio context. This makes it roughly 20 times faster than autoregressive text-to-speech systems. It can also do zero-shot voice cloning by conditioning on a short audio clip of the target speaker. Third, robotics. Pi0 from Physical Intelligence, released in 2024, uses flow matching to generate robot action trajectories. The velocity field operates over joint angle space, and the model is trained on diverse manipulation tasks, folding clothes, pouring liquids, assembling objects. Because FM needs only 10 to 50 sampling steps, it can run at the 10 Hz control frequency required for real-time robot manipulation. The bottom diagram shows the key point. Flow matching is a general-purpose framework. The same mathematical recipe, define a probability path, learn the velocity, solve the ODE, applies across all these domains. You only change the state space and the architecture. Now let us talk about what goes wrong in practice and how to fix it. This is the kind of knowledge that papers do not usually share, but that saves you days of debugging. The first common problem is that samples look noisy or blurry at the end of generation. This usually means you need more sampling steps, or your Euler solver is accumulating too much error. Try increasing the number of steps, switching to a midpoint solver, or double-checking that your time range actually goes all the way to t=1. If your training loss is stuck at a high value and not decreasing, the usual suspects are a learning rate that is too high, a network that is too small, or incorrect input normalization. Flow matching requires that the velocity targets have reasonable magnitude, so make sure your data is properly normalized. Mode collapse, where all your samples look the same, usually means something is wrong with your noise sampling. Verify that x0 is actually drawn from a standard Gaussian and that your batch size is large enough to cover the data distribution. If your samples always drift towards the mean of the data, classifier-free guidance is probably too weak or your time variable is not reaching 1. With the x1 prediction parameterization, you may also need to clip t away from the boundaries to avoid singularities. NaN values in the loss are almost always caused by singularities in the velocity parameterization. The x1 prediction and x0 prediction formulas have singularities at t=1 and t=0, respectively. Clipping t to the interval epsilon to 1 minus epsilon usually fixes this. The single most important debugging tool is trajectory visualization. Plot xt at several time points for a small batch. If the trajectories are straight and non-crossing, your model is healthy. If they are tangled, curved, or collapsing, something is wrong with your coupling or your model capacity. Let us wrap up Lecture 5 with a summary of the practical toolkit we have assembled. Today we went from theory to practice. We started with a complete end-to-end implementation of flow matching on the 2Moons dataset in just 30 lines of code. We discussed the two dominant architectures, UNets and diffusion transformers, and why DEET has become the preferred choice for scaling. We explored noise schedule design and the important scheduler equivalence theorem. We saw how the flow matching library handles all the mathematical plumbing. We analyzed the quality-speed trade-off in sampling steps and the hierarchy of ODE solvers. We demonstrated how Minibatch OT produces straighter paths and better samples. We surveyed the state-of-the-art systems for images and video, and we explored applications beyond vision in proteins, speech, and robotics. Finally, we compiled a practical debugging guide for common failure modes. If you take away one thing from this lecture, it should be the practical FM recipe on the right. Use conditional OT paths for simplicity, use mini-batch OT coupling for straighter trajectories, use a DEET architecture for images, train with the velocity parameterization to avoid singularities, sample with a midpoint solver at 25 to 50 steps, add classifier-free guidance for conditional generation. In Lecture 6, we leave flat Euclidean space behind and enter the world of manifolds. Many important data types, protein backbones, molecular conformations, data on the surface of the Earth, live on curved spaces where straight lines do not exist. We will need a gentle introduction to Riemannian geometry and will develop geodesic conditional flows as the natural analog of our linear paths. Our running example will be flow matching on the 2-sphere, the manifold analog of our 2Moons dataset. See you there.